Okay, some notes about solving to find x-intercept. So in general, any type of equation, quadratic or not, in our solving to find x-intercepts, there's a basic idea of what we do. We're setting y equal to 0 and we're finding x, because that's what we know about an x-intercept. We know it's a point on the x-axis, which means the y would be 0. Our focus right now is going to be on finding them in vertex form. Next week, we're going to focus on finding them in standard form. In standard form, you should technically already know how to do the quadratic formula and factoring and completing the square, though you may need reviews of all of these. And we're going to review them, factoring a little shorter, as well as quadratic formula. We'll spend a little more time with completing the square. So those are ways to find the x-intercept for standard form. When it's in vertex form, you could multiply it out to standard form and use any of those things. However, vertex form is unique in the fact that the way that it's written houses all of the x's within the squared of the function. And you guys actually know how to solve functions that are squared. So if I just had an equation that says something like x squared equals 25, you could solve this by square rooting both sides, and you would get that x is equal to plus or minus 5. Okay? If we made it slightly more complicated, if we had x plus 1 squared equals 25, we could still do the same thing. We can square root both sides to get x plus 1, and the square root of 25 was plus or minus 5, and then we'd subtract 1, and you'd have a positive 5 minus 1, which would be 4, and a negative 5 minus 1, which would be negative 6, and you'd get two solutions for that. So when we see that perfect square in our equation that contains all of the x's, that x only exists inside the perfect square, not beyond it. So that's why it doesn't work for standard form. Here we have an x that's part of a square, and then here we have an x that's not. In vertex form, our x's are all part of the perfect square, which then we would kind of want to use those square roots, but we can't do that until we isolate the part that is squared. So let's say we have an equation that maybe looks like this. Oops. So we would go ahead and we would really work to isolate this radical. So we would actually add 8 to both sides. And this is after we've plugged in 0 for y. Then we would divide by 2 to cancel that a value of 2. And we'd have that 4 equals this perfect square. Now, in order to get rid of that perfect square, the squaring portion of it, so that we can move around some of the variables and constants that are inside of that perfect square, we're going to want to do the inverse of that, which is take the square root. So on the left side, we will get plus or minus 2. On the right side, we will get 1/4 times x minus 1. Now, what to do next is to finish solving the equation like normal. If this was your equation and you wanted to solve for x, you'd want to cancel out the 1/4, so we can multiply by 4, and then we have to do it on the other side as well. So now that side will become plus or minus 8. This will have canceled this out, and we have x minus 1. And then we'd want to add 1 on both sides. So we would have that x equals 8 plus 1, which is 9, or negative 8 plus 1, which is negative 7. If that 8 had been a more difficult number, so let's say that maybe that number had been a 10. 10 divided by 2 would have been 5. The only difference here would have been that you were working with a radical, and then that would make it not easy to combine these values, and you would write your answer a little bit different as 1 plus or minus rad 5.